Hello seniors, it's been a while and I'm glad to see you all again. Another journey is yet to overcome. Let's step ahead in learning another exciting area in science that concerns with the study of inanimate natural objects, including physics, chemistry, astronomy, and related subjects. Students, it's time to learn physical science. Our lessons today is limiting reactant and chemical reaction. But before that, at the end of this module, you should be able to determine the limiting reactant in the reactions and calculate the amount of product formed. Use stoichiometric calculation to determine excess and limiting reactants in a chemical reaction and explain why. And the last objective will be calculate the theoretical yields of products formed in the reactions that involve limiting reagent. Before we proceed to the discussion proper, let's have these keywords or the key terms. Okay, so we have here the three terms. The first one we have here, the stoichiometry, is a branch of chemistry that establishes mole and mass relationship between the reactants and or products in a chemical reactions to determine the desired quantitative data. The second one we have here, the excess reagent or the reactant rather. It is a reactant that is not used up when the reaction is finished. The third one, we have here the limiting reagent or the reactant. It is a reagent that is completely used up in a chemical reactions. You and your friends plan to have a beach picnic. They asked you to bring barbecue on your picnic. You decided that each stick of the barbecue has 3 slices of beef. If you have 36 slices of beef and 10 barbecue sticks, how many barbecue can be made? Okay, so from the 36 slices of beef and 10 barbecue sticks, you can make 10 beef barbecues because there are 3 slices of beef in each sticks. Although you can make more barbecues from the remaining slices of beef, only 10 barbecues are possible due to the limited number of sticks available. In this scenario, sticks are the limiting reactant since it all used up in the process. Well, specifically, 6 slices of beef are the excess. This refers to the excess reactant simply means not used up or the leftover in the entire processes. How do we know if the reaction is totally stopped? Okay. Oh, good. The reaction will stop when all the limiting reactant is already used up. In a given chemical reactions, there is a limiting reagent or the reactant, and to which determines how many products are to be produced. Limiting reactant is a substance. So it shows first used in a chemical reactions. These reactions always serves as the basis for calculating the quantity of a chemical deformed product. But how can we determine a chemical reactions with a limiting reactant? Let us try this experiment. Suppose you have 4.5 grams of aluminum and 2.25 grams of sodium chloride. Initially present, so find A, the limited react, and B, the excess reactant remains after the reactions, and the C, the grams of the aluminum chloride formed. The first step is to write the balanced chemical equation for the reactions described in the problem. But how do we know that the equation is balanced? Okay, so you're right. Both the total reactants and the products have equal numbers of the elements. So for these specific equations or the situations, we have these equal and balanced chemical equations. So aluminum plus 3 sodium fluoride will lay you the aluminum chloride plus 3 sodium. Okay, so the number of the aluminum, sodium, and the chlorine in both sides are in the left and the right sides of the equations are the equal. Now, if you're having difficulty in balancing chemical equations, you may watch the related video about the balancing chemical equations. Okay? Now, for the second step, calculate the molar mass of the reactants again. So we have aluminum equals 27 grams per mole, and the molar mass of the sodium chloride is 58 grams per mole. 58 grams per mole is obtained sum of the molar masses of the sodium and the chlorine. For the sodium have 1 times 23 equals 23 grams per mole, and for the chlorine is 1 times 35 equals to 35 grams per mole. And a total of 23 and 35 is 56 grams per mole of the sodium chloride. Okay? So, for the step 3, divide and calculate the molar mass of a given element or compound from the given mass. Then the number of mass are divided by the coefficients indicated in the balanced chemical equations. So, how are we going to do this? So, let's check this out. This is the step or the step 3. The question is, can we divide it into 2 parts? Yun. So, let's take the first point, that is divided the calculated molar mass of the given element or compound from the given mass. Okay, so you know, in a given example, you can see that the mass has we have the given mass of 4.5 grams, and its calculated molar mass is 27 grams per mole. So the 4.5 grams divided by 27 grams per mole equals to 0.167 moles in the sodium chloride case. So we have 2.25 grams, that is given mass of the sodium chloride, divided by the molar mass, or the 58 grams per mole, which is equals to 0.039 mole. Well, the second part of this step is to divide the number of moles by the coefficients indicated in the balanced chemical equations. So let's have this for the aluminum: 0.167 moles divided by 1, which is coefficients of the aluminum in the balanced chemical equations, which is equals to 0.167 moles for the sodium chloride. So we have 0.039 moles divided by its coefficients in the balanced chemical equation, which is 3 equals to 0.013 mole. So analyzing the results, so we can say that the limiting reactant in the sodium chloride, since the calculated value is 0.013 lesser than aluminum. Well, the aluminum shows calculated value of 0.167. Therefore, it is concluded that the aluminum is the excess reactant, since there is more than enough of it to react to the sodium chloride. And for the last part of our example, we will find the grams of the aluminum chloride. For first, we have to get the molar mass of the aluminum chloride. Okay, so aluminum equals 27 grams per mole, and for the chlorine, we have to multiply the subscript, which is 3 by 35.5, which is yield the 106.35 grams per mole. So let's get there. In the sum of 27 grams per mole plus 106.35 grams per mole is equals to 133.35 grams per mole. Next, we will use the stoichiometric method, and we will have these questions. Chemical reactions in the real world don't always go exactly as planned on the paper. In the course of an experiment, many things will contribute to the formation of less product than predicted. Besides spills and other experimental errors, there are usually losses due to an incomplete reactions and besides both sides actions, etc. The gametes and need measurements that indicates how successful our reaction has to be. This measurement is called percent yield. To compute the percent yield, it is first necessary to determine how much of the product should be formed based on the stoichiometry. This is called the theoretical yield or the maximum amount of the product that can be formed from the given amount of the reactants. And the actual yield is the amount of the product that is actually formed when the reaction is carried out in the laboratory. The percent yield is the ratio of the actual yield to the theoretical yield expressed as percentage. Percent yield equals the actual yield divided by the theoretical yield times 100. Percent yield is very important in the manufacturer products. Much time and money is spent improving the percent yield for the chemical products. When the complex chemicals are synthesized by the many different reactions, one step with a low percent yield can quickly cause a large release of the reactants and unnecessary expenses. Typically, percent yields are understandably less than 100% because of the reasons indicated earlier. However, personally, it's greater than 100% possible. If the measured product of the reactions contains impurities that causes it's much greater than its tactfully would be. If the product was pure, where the chemist synthesizes desired chemicals, he or she is always careful to purify the products of their reactions. Alright, so let's have this example. Potassium chlorate decomposes upon slight heating in the presence of the catalyst according to the reactions below. Or these reactions in a certain experiment, 4.0 grams of the potassium chloride is heated until it completely decomposes. The experiment is performed and the oxygen gas is collected and its mass is found to be 14.9 grams. Number one, what is the theoretical yield of the oxygen gas? And number two, what is the percent yield for the reactions? So let's start with the calculations of theoretical yield. First, we will calculate the theoretical yield based on the stoichiometry. So the first step to identify the given informations and what the problem is asking you to find. So our given data or mass of the potassium chloride, which is 40.0 grams, and the mass of oxygen gas collected, which is 14.9 grams. And to identify or the quantity being asked is the theoretical yield or the grams of the oxygen. So for the first step is to list other known quantities and plan the problem. So 1 mole of potassium chlorate is equals to 122.55 grams per mole, and the 1 mole of the oxygen is 32 per mole. So the third step is to apply the stoichiometry to convert from the mass of the reactant to the mass of the product. So in this specific example, from the grams of the potassium chlorate to mole of potassium chlorate, we have this ratio of 1 mole of potassium chloride divided by 122.55 grams of the potassium chloride. So from mole of potassium chloride to the mole of oxygen, we have 3 mole of oxygen divided by 2 mole potassium chlorate. And then, excuse me. And then 2 grams of, or 32.00 grams of the oxygen divided 1 mole of oxygen. Okay, so the for the fourth step, you have to solve. Okay, so you have to solve. Okay, so that theoretical yield of the oxygen is 15.7 grams or 15.67 grams pag siya ay hindi man unrounded. Okay? So for the step 5, think about your result. Okay? So the mass of oxygen gas must be less than 40.0 grams of the potassium chlorate that was decomposed. Now, we will use the actual yield and the theoretical yield to calculate the percent yield. Okay, step, identify the given informations and what the problem is asking you to find. So the given for this specific example, the theoretical yield equals 15.67 grams, and the grams use the unrounded number for the calculations. Okay, unrounded po. And then the actual yield is 14.9 grams. Okay, so what you are looking for is the percent yield. So the step 2 is to list other known quantities and plan the problem. No other quantities needed. Okay, so the step 3 is use the percent yield equations. Again, the percent yield equals the actual yield divided by theoretical yield multiplied